Have you been recording the tutorials yourself recently, or?
I have, yeah.
Oh, that's so fun.
Not recently. We're doing a pretty big rework of all of it. So right now you do like a parametric power regulator as your first design.
Yep.
And then it's going to be like gigabit Ethernet switch as your first design.
Okay.
And try to hit it in like an afternoon.
For everyone who wants a custom gigabit Ethernet switch.
Yeah. Which is everybody.
I don't know if switches are like routers are actually a fun first project. I guess switches and routers are kind of two totally different things here. Showing my.
I mean, a router has a switch. Like you got the 4 ports in the back. Right?
Yeah, like with OpenWRT and stuff like that, it's a really fun first project because you can get like a small Linux system in many cases. I don't know. Do most is your tutorial going to include like Linux on that board, or?
It's more of a microcontroller based design. So this is you have a switch on there so you can daisy chain Ethernet through it. So then you can network like 100 microcontrollers.
Yeah,
I was going to ask. So it's
sensors,
base 2,
industrial interfaces, or you could it'd be optical. Ethernet. You can do all sorts of stuff.
Okay, so what media what physical media would you typically run in the first tutorial? Would it be the classic RJ45 Ethernet cable, or are you doing base 2 gigabit Ethernet like you use in industrial and cars these days, or?
Yeah, probably. I think the design is more industrial focused.
Yeah, nice.
Yeah.
It's interesting. I mean, I'm sure you've seen plenty enough of it, but obviously the Cybertruck was released with no CAN buses anymore. It's all Ethernet.
Oh, okay.
And a lot of things are tending that way because we're trying to fling enough data in real time, deterministically, around our cars that all of a sudden you look at whatever it is, 10 megabits that you get out of CAN FD as being piddly, and what could you possibly do with that? And so we bump it up to gigabit Ethernet to stream typically just real-time telemetry around the cars. It's not even the video feeds that are going over something like that.
Yeah, real-time enough, right? Because Ethernet doesn't have those guarantees. But then in practice, it's fast enough.
It depends what layer you get to, because EtherCAT, for example, makes the guarantees. And that uses, obviously, the physical layer.
Yeah.
You go up and protocol as well, I believe. No, sorry, it's the protocol layer they cut off. And it basically runs the packet around the bus, daisy-chained as a big train, and it just swaps out a set of bytes that each thing's allowed to talk to. But if you make an EtherCAT controller, then I'm interested, because I wanted to put one in robots for years, and it was a pain in the ass.
It still is. Yeah, so a lot of the robotics labs have moved to Ethernet, but they don't bother with the overhead of EtherCAT.
Okay.
Because it's fast enough, right?
Yeah.
You can get like 100 devices at a kilohertz, like loop closure rate.
Yep.
Ish. You just got to hit, like, it might skip a couple cycles. You just got to be robust to that.
Well, it depends where you place your controls as well, right? Because if you put, depending on where you put your various levels of control loop, you might have, you can think of it as a human. We have 80 milliseconds of latency between where we perceive the world and where we actually place ourselves.
Sure.
Whereas if you have, maybe say a CNC machine, you have a deterministic path. If you provide that path as a, say, at this date and time, you need to be here, each of the axes, it can perhaps follow that path without needing a deterministic centralized controller to coordinate those axes beyond that, for example.
Yeah. If you wanted to bring distributed systems into your robot, in case it was too reliable.
So just like thinking through, I haven't done anything in robotics, maybe like a tiny bit, like a long time ago. What are the different solutions when you're looking at networking all the sensors on robotics? Like, so you have the CAN bus, and then you, I guess, can do this kind of Ethernet setup, and it seems like there's even a couple custom choices you can do in there. So what do people use in practice? What are we moving towards?
Yeah, I mean, CAN was the leading one for a while, and you still do a lot with CAN.
Yeah.
But then, I've been seeing people move more towards Ethernet.
Okay.
Yeah.
Okay. And so do they like literally buy, like you're literally buying like a router and putting it inside the robot?
It's not too far from it. You'll use like a off-the-shelf switch IC, and you'll probably use a lot of the similar, Linux kind of stack that you normally would, because it maintains all the same protocol. But instead of what if you think of a regular Ethernet cable, like an RJ45, the blue cables you'll string around a building everywhere, a lot of the industrial Ethernet uses actually just a single twisted pair to transfer all the data around. So much less cabling, but you still get gigabit Ethernet through it, and you do so reliably with I think the base 2 is a relatively new standard as well, actually. But it's intended for this kind of industrial robotics or automotive use.
Okay. All right. I'm just gonna keep asking questions. There's a lot of new terms here. Base 2, what is this?
The fact that there's two copper conductors.
Gotcha. Okay. And then when you're doing this on a robot, does every sensor get an IP address? What's going on here? No, we're not that high in the stack. Okay.
Look, some people I'm sure might have tried that, but I probably wouldn't necessarily recommend it myself. Yeah. What have you seen? You've probably seen more of it firsthand from your robotics background.
You take like a Ethernet switch IC and has at least 2 ports, so you can daisy chain it through. So you have like a robot arm, and you don't have to run 9 cables. You can run 1 cable. And then typically you'll network a microcontroller to that. So something that supports RJ-MII, or no, RG-MII. Like a ST micro part, like STM32F4, for example. And then you can network a bunch of sensors in communication to that. And then you route that as far as it's useful, right? So if you have like a robot hand, I've seen some with like 17 microcontrollers in there. So they have like much more distributed programming, or you could have 1 and more cabling, but usually cables are the worst.
So 17 microcontrollers in just the hand.
Yeah.
Wow. Okay.
This was we used to be a design consultancy when we were prototyping the technology, so we redid some stuff.
Yeah.
So you were the ones that put the 17 microcontrollers.
No, we were handed this as like, here's a problem. We want it to be better. Please redo all of the electronics.
Oh, I see.
Nice.
Yeah. Makes sense. Huh.
Were these sort of breadboard microcontrollers off eBay, and then they said, hey, could you consolidate it? Or
no,
it's serious micros?
Most robots are kind of they tend to be a pile of small steps, like very evolutionary. It's like, okay, we need to drive this motor. It's like, okay, we need to drive a smaller motor, and now the inductance is too low, so we're going to like stick an inductor on top of the motor driver, and we'll find one that kind of fits, so you don't have to change the board very much. And then, okay, we need this other sensor, so we're going to kind of like stack another sensor board on top of this. So it kind of becomes a hive of things, because they don't really redo the design once they figure things out. But it has to evolve very fast because you got a robot touching the real world.
This sounds like a spaghetti code base, but just in hardware.
Yeah, big spaghetti tower.
Right. That's pretty cool. I feel like we're a couple minutes in now, but we haven't intro Duncan. You know, we introduced ourselves in the first episode, but Duncan's here. He's from jitX. jitX is like I don't want to downplay us, but it's probably the #1 electronics as code language / platform right now. Duncan's shaking his head.
I mean, if you look at a system design, sure, like circuit boards, systems of circuit boards, digital chips have been electronics as code for a while.
Right, that's true. That's a good point.
Synopsys is pretty big.
So at the board level, jitX right up there, trophy 1. But at the chip level, Synopsys is the victor. And I don't know how many people are competing with Synopsys on that layer yet. Is anyone?
And that's the nice thing about EDA is you have like 2 public companies.
Right.
You have Synopsys and you have Cadence. The number of new public companies is -2, so it's easy to keep track of.
That's true.
It's not like cybersecurity where you have like a 500.
It's only 2 choices. Yeah. Only 2 choices. But Duncan, thanks for being here. Duncan, you have a super interesting background. I listened to you a little bit on the MacroFab podcast. You went through a PhD program. You built a crazy jumping robot. Super cool. I'm really curious about sort of the origin of jitX, like just kind of your background for all the people listening and who might not know you yet, listening to an Electronics as Code podcast.
Sure, yeah. So, like you said, prior to jitX, I was getting my PhD building robots at Berkeley. And Berkeley is very collaborative. That's actually why I went there. They had a program in sort of bio-inspired engineering of like, how do you get a diverse group of people together, and how do you get like experts working together on research in the way that's actually productive instead of what usually happens, which is nothing. So I built bio-inspired robots. I was taught to be a scientist by the biologists, so I could like do research and be systematic about things. And then I'd find a concept I wanted to test. I worked on robotic locomotion. How do I make better running robots, better jumping robots? So I found like this monkey's weird knee looks like it helps it jump well. Because most things jump a meter, right? So a flea jumps about a meter, and LeBron jumps about a meter. And this Galago...
Watch out, LeBron. He's coming for you.
Well, maybe you've seen those exhibits as like, if a flea was human-sized, it would jump over a 70 stories built. Yeah, no, it would jump about a meter. because that's
So, like,
how
there's,
scaling
like,
works.
There's like a speed of light, and it's a meter. Just if you're a living thing, you're probably just gonna jump a meter high.
Yeah, you have these sort of non-dimensionalized scaling laws, and you can just kind of apply them and figure out. It's like, okay, when things grow in length by a factor of 2, they grow in weight by a factor of 2 cubed, because that's how volume works, right?
Right.
Then you can also apply this to dynamics and muscle areas and figure out most things jump about a meter, except for this monkey, the Galago, which is a bush baby, so it's the one with like the big cute eyes.
Oh,
Yeah, and it jumps 2 meters. I was like, well,
Crazy.
yeah, well,
an
that's
anomaly.
This is pure vertical jump, like from
Yeah.
a standstill.
yeah, it leaps like a freak.
Right.
Not to derail too much, but why? Why are they jumping so much? They escaping predators, getting into trees.
All sorts of stuff. Yeah, and with animals,
not
you
flapping
usually have to
during
guess. No, gliding.
No
Skin
gliding, okay.
flaps, no.
Okay.
So for anyone who's not in the metric system, 2 meters is about a standard door frame high, roughly speaking. It's about 6 feet.
That's good. Yeah. So my robot weighed 100 grams, which I explained to Americans is like it weighs about as much as a stick of butter. So anyway, yeah. So I could come up with a concept and see like the mechanics of, okay, here's this sort of special series elastic mechanism with this leg, and you can load it like this, and it should be able to jump, but very powerfully and very controllably. And then I spent all of my time as a hardware engineer, right? Because I was just like designing this robot, full custom electronics, firmware, mechanisms, materials, manufacturing process.
Did you have to do that? Like, were you like,
Yeah.
everything is bad?
Well, I was pushing the performance bound.
I see.
And this stuff you can't buy off the shelf.
Roughly
Right.
what year was this as well?
That research started like, I don't know, 2014. I
Okay,
guess.
so this is like pre-ODrive, pre some of the like more modern open source sort of motor control projects. Maybe like the VESC was just roughly 2014, something like that.
Maybe. Yeah.
Okay.
So those are
Yep.
getting started, but they're still larger.
their infancy, yeah.
Yeah. And like, I didn't know how to design boards at the time. So I tried to buy, I bought something off the shelf, like the smallest controller I could get.
Yep.
And it was still 20% of the mass of the robot.
Yes.
Wow.
Nice.
Yeah. And you're trying to jump, so you don't want to be heavy, because I want to jump high. Yeah. So I kind of got, to start that project, I threw away from everything from my previous robotic project, which was like a running cockroach robot. And that sucked. Like in hardware, you can't reuse anything. And then, but I could do it, right? I could do the hardware design, I could do the work, I could iterate,
Right.
I could build these robots.
Right.
But then I would go to a conference and you see people who don't have those, like the same skills, because I had peers I could learn from, and they are a smaller program. And they couldn't do as much science. I was like, well, that sucks. So I open sourced my designs.
Nice.
And nothing happened.
Oh,
Because open sourcing in hardware is like not that meaningful
Yeah.
right now, before it's code, right?
right.
Well, it's not really source. It's just kind of open artifacts.
Yeah, open artifacts is a good way to describe it. It's like
Yep.
the GitHub for assembly code. It's like not as good.
Yeah, people would love it. I mean, didn't we call that SourceForge or something?
No.
Oh, where with like
No, what-
binaries and whatnot.
Yeah, it wasn't. They actually had the source code, but you kind of had to get to it a little. It was a bit hard.
Yeah.
I only ever downloaded artifacts from it. So
Wait, where did you upload the code out of, or the artifacts out of curiosity?
Yeah, I put them on GitHub. I referenced them in the papers that I was writing.
Gotcha. Gotcha.
And it didn't really matter.
Yeah.
Because if anyone wanted to change anything about that robot, they'd basically have to be able to redesign it from scratch.
Right.
Because that's the story in hardware. Your context for what the design is not in the design. You really only have artifacts.
yeah.
Yep. Yep.
So that kind of sucked. I saw people doing less science, and I couldn't even share my work with them. And I saw like these great labs in Germany. It's like they really know how to do a robot arm or a variable stiffness actuator, and the one at Stanford is really good at controlling it, but they will never collaborate because hardware just doesn't allow that.
right.
So I got seeing all the science not done. I got really fed up. And then like colleagues in neuroscience, they couldn't do their research because they wanted a slightly different circuit to measure the brain, and they had no capabilities to design
Right.
electronics.
Right.
And then I met my co-founders and got introduced to the world of like digital logic design, where automation is given, right? You write code, you compile it, it gives you a design. The design is simulatable, it's checkable, right?
I'm not dragging and dropping 26 billion transistors or whatever NVIDIA just put on the
Yeah,
that's right.
Exactly.
Yep.
And optimization is like the norm. Because the research is like, oh, I'm going to make this like visual pipeline for like SIFT identification so I can do like optical flow or whatever. And then I'm just going to optimize it, and I can just find the best implementation just by searching across this space. And that's like the norm. And I looked at hardware design and our like manual drawing tools where you don't get to reuse anything, and like optimization is so far away. It's like, well, this is not okay.
Right. Right.
So yeah, I talked to some of their grant collaborators at the time. So they were working on a DARPA program called CRAFT. And CRAFT was, how do you 10x design productivity for chips? Even with a language, it was still Verilog, right? Which is not a productive language.
Yeah.
And so people don't write Verilog, they write like Perl that manipulates Verilog.
Right.
So my co-founder has a product called Chisel, which is like, what if you had like an actual programming language, right? Like a real one with parameters and reuse. And that worked really, really well. So Google used to tape out the TPU. There's this company called Sci5 that like using Chisel as like their main.
I did not know that Google Touch. Well, that's relevant for another topic today.
Yeah. And so specifically, Chisel was for like digital logic design, not place and route. It's like high-level synthesis, get the reuse much better than Verilog. But their grant collaborators were Northrop Grumman. So I did the startup thing. It was like, I would interview designers and figure out what they want.
Yeah.
So I interviewed them. I was like, oh, what kinds of things do you design? And they were like, well, have you ever flown out of SFO? I was like, yeah. And they're like, well, we designed the radar system. I was like, oh, man.
Whoa.
This is some real stuff.
Yeah.
Right? Like the thing that stops all the planes from running into each other is like what they work on. And the next thing he said is that my team runs on decades of experience in human designers that can walk out the door at any time. And I was like, well, that sounds bad. The world suddenly felt much more fragile. Yeah. Right? So that same problem I had of like, well, I can't reuse anything and my knowledge is not in my design. Northrop has all the money they want to spend on tools. Right. They have exactly the same problem at drastically higher levels of complexity. Right. So this seemed like a problem that needed to be solved. It was, as far as I could tell, the most impactful thing I could do.
Yeah, that's so interesting that like the knowledge and design intent is just trapped in humans, right? Like if I go to GitHub and I pull a code base and I start to try to contribute, I could probably not only figure it out, but I could probably figure out intent, like all the function names kind of contain things that tell you what they're for and stuff like that. But hardware, drag and drop hardware design is a lot more like this is just data. Like we're just telling you the result of us doing a lot of research and part selection and reading data sheets and all of this. So you saw this as a huge problem and then you're like, all right, we're going to tackle it. So you rallied your co-founders and then I guess
yeah, we just liked working together, so we kind of did it as a skunkworks project while we were still at Berkeley. Oh, nice. Actually started on the mechanical engineering side, which was my background. So yeah, we taught a class on computational design and taught a bunch of like CS students how to design stuff, and we walked from like one-dimensional fabrication, which is like bent wire structures, through 2D, which was sort of laser cut and folded structures, and 3D and 3D printed, and then how do you generate designs across that whole space.
Whoa, wait, so you were generating mechanical designs?
Yeah, this was the first class we taught together. Yeah.
Whoa, okay, so okay. All right, so walk me through this again. So you start with bent wires, one-dimensional. Yeah. What do you do with why do people want to design bent wires?
Because it's amazing. So your supply chain is just like this big spool of wire, right? So it's like 3D printing, but it's much cheaper, and you just get to use steel, and it's like way faster. Okay. It's like there's a reason like coat hangers are made out of bent wire. Like it's fantastic.
That's true.
Or like those, little bottle plug things. That mechanism where you can like pop up a bottle open.
Oh yeah. Okay.
So like if you can make it out of bent wire, like you're doing good. Because it's steel, it's cheap, and it's just like a reel of stuff.
I have never, wow, I feel like I'm learning like a new underlying like thing, because I see sheet metal all over the place and I think, oh yeah, sheet metal, that's like a great material, but I never think about bent wire. Yeah. I'm gonna see it now when I walk around. Be like, that's bent wire. I can make that.
Yeah, and that's like one thing I wanted to bring to hardware engineering in general is like sharing methodologies is so hard. You have to like apprentice or journeyman with someone to like learn a technique.
Yeah.
And then you can do it. And like, but compare that to the knowledge dissemination in software and code. Like, oh my God.
Yeah.
It's very much monkey see, monkey do, where I'm the monkey, and unfortunately, I'm not that smart. So if we could kind of scale that to a level of more humanity, where with code, I actually don't really need to know what's going on in the guts of everything. That's where you get the force multiplier there.
Have you guys ever seen this meme where like one like cartoon gives another cartoon something, and then the guy goes, "I made this," right? Software is just like, you can take somebody else's work and then just say it's yours. Like I took a React component that made a beautiful table. I throw that on my landing page and go, table.com. It's all me, but you're just using a bunch of people's software underneath. There is no equivalent for that in hardware. You basically have to know what your hardware is doing, right? At least with drag and drop.
And they might even have their name stamped literally on that hardware on your landing page as well.
Yeah, yep.
Yeah, no, you have to steal the whole design, and then you tend to get in trouble.
Yeah.
We talked about the legality aspects of this in the last episode, actually.
Yeah. I don't want to resurface, but too much. But we were talking about how if you software is kind of considered free speech because kind of text is generally considered like you can release almost any text and it's like free speech and you can put it in a book and whatever. But with diagrams and hardware, there's a lot more protections around it, it seems. So it was topic for last time. I don't know if you have any hot takes on that, kind of in the licensing world, new innovations you can do now that the circuit board is kind of in code, Now it's in free speech material.
Yeah, I mean, I've always seen software, like if you want to make something open source, you have to put a license on it. It's like uploading the code does not really make it open source. Like,
right.
An open source license is what makes it open source.
Right.
And you can put that on whatever you want.
Specifically, though, so back in the day, strong encryption was considered an ordinance, and there was a famous case in the 90s with Zimmerman that made that defined as free speech. They found that with a high-level programming languages, there's no difference to French or German. Now, by bringing designs, particularly as you're discussing from defense manufacturers in the US into code and a high-level programming language, I wonder how ITAR now applies to those designs.
Yeah, this is why JitX runs locally instead of in the cloud. I don't want that data.
Yeah.
Well, you don't want the data, but I wonder actually maybe it's a welcome by your suppliers if they have offices elsewhere in the world. They might actually be able to do things, transfer things internationally they weren't previously able to.
I don't think our design tool is like the big blocker for that.
If people want to transfer things, they're going to transfer it in the closed source world, behind closed doors. Yeah, makes sense. Something I've been curious about, especially because Matt and I are kind of newer companies in the electronics as code world. What were your early customers like? Where did you start to find the gears of traction with jitX?
Sure. So coming out of Berkeley, we did the usual academia thing, which is like get a DARPA grant. I guess in your company they call it a contract. So I got a DARPA contract, and we actually partnered with Northrop Grumman, so the same sort of team that been developing those radar systems. Like, okay, we want to work on automating circuit board design, and DARPA was like, that's a good idea. Start with military satellites, please.
Really the hello world of circuit board design.
Yeah.
And with DARPA, is it an II captain? They're naval, if I remember correctly, or how do you say yes, sir, to DARPA?
I mean, it was very much a research type collaboration. So something quite similar, like we were research PIs, principal investigators, had program goals. You go give demos. With DARPA, the demo is always the most important thing.
Did you hit compile and then there's some little green tick in the terminal and they went, okay, did it work? And you go, oh, yeah, we promise it did.
Yeah, so we actually generated, we were using some image generating framework, GraphViz, I think.
Oh, yeah.
So like we had a GraphViz schematic.
Oh, fantastic.
And you can cut that at like various levels of hierarchy.
Yep, for sure.
Cool. So graph is for, I guess, listeners, is kind of like, it's almost like something commonly used with LaTeX to make diagrams. So this would have been, I think you can make pretty good looking schematics with GraphViz.
It's a kind of a general.
I'm completely wrong. So it was like a node graph or something.
It is a node graph. It's just not a good looking schematic. At least according to our users are electrical engineers, right? Primarily. Like they'll have a background in that. They know what a good schematic to them looks like. And they have specific stylistic goals that are not fulfilled by anything I was able to buy. So we had to build.
Fair enough.
Yeah. Hey, guys, can we pause for just a second? I think we're getting a lot of noise through
the window.
Oh,
from the window? Yeah, let me get that.
I'm hearing some banging as well.
Who's banging? Sorry about that.
Perfect. Okay. That's a lot quieter.
That's a lot quieter.
Hopefully we continue from here. So the stylistic goals, because I mean, this is actually an interesting point because typically electrical engineers use the style as part of the description of what their intent is. They'll orient a component depending on, things will flow left to right logically or down the page in terms of voltage typically. These are common concepts and they're kind of schematics aren't really that legible if you kind of don't follow them.
That's right. Yeah.
And so were you able to, compile them in a way that humans love them, or do you still end up having to have people tweak them to capture their sort of intent into the diagram?
You do both, right? So you can do a lot of optimization up front. When you have code as an input, you actually capture a lot of your context about the design for free. Like you're not just dealing with a net list, which is a garbage input.
Right.
You actually know what the circuits are for and what makes them good and what the meaning is and what the voltages are. Like all of that is available data.
Preach into the choir.
Yeah, right. But then also you find people want to tweak it, right? They'll even like styles vary across engineers, and there's no universal style where like this is the good schematic. So we built a UI so they can move the schematic around, kind of rearrange the style, but it doesn't change the connectivity.
Yep.
It just changes the style.
Do people in jitX, and I haven't tried out jitX, I'm very excited to, but when you're moving like these schematics around, is it kind of like figuring out all these traces? So it's figuring out all these trace connections. It's like easy to do. So you're putting in automations, I guess, wherever possible to, I don't know if this is always the case, but like a lot of times when you drag around, and I'm used to older programs, but like the lines don't move, so you gotta like move the lines again and all this. You know what I mean?
No, sometimes I go back to using like Altium or KiCad, and I move something and nothing updates. And I'm like, oh, I forgot.
Yeah.
So like all of in the schematic, the wires are drawn automatically. In the board, the traces are drawn automatically. So when you move something, everything just updates because of course it should.
Yep.
Right.
Yep.
Yeah.
Yeah. It's just like a lot of the older software. And I guess like I haven't used some of the newer drag and drop. I think Flux is kind of the new guy on the block as far as sort of drag and drop EDA tool land.
Every time I've touched them, they're UI's been the probably premier, best polished.
Really?
Yeah. Yeah.
Okay.
It's fantastic. Like, Altium, Cadence, anything you open from a couple of decades ago kind of typically has a UI that's rooted a couple of decades ago in like the Windows components and that type of thing. They've got a good design team over at Flux.
I think they got design founders as well.
Yeah,
right? So
absolutely.
Been, like day one.
Yep.
The problem with circuit board design is the design tool.
Yep.
And it's not online enough.
Yep. Makes sense. All right, so I guess I'm tempted to get into EDA tools, but before we do that, some timely things that sort of happened this week. I don't know if anything interesting happened to you guys this week. Something very interesting happened in the world regarding computers just randomly shutting down. And I'm curious if you guys saw that. I'm talking about CrowdStrike. CrowdStrike did some kind of kernel patch on a bunch of computers. It all went down. I'm curious what your guys' take was on this, and what does it mean? What does it mean to you? What's your hot take?
As far as the interesting things to me personally, I have a Mac, so I didn't actually notice until Mum texted me and said, "Hope all is well." I hope all is well with you too, Mum. Is everything all right?
Yeah, no, we're all on Macs or Linux. It's
Oh,
nice
really?
New design tools is like, you can make it work on a Mac now.
Yeah.
Thank God.
But a lot of our users are on Windows. They seemed okay. I didn't need to use any emergency services or fly anywhere. So
the emergency services were all down, hey?
not all of them, but definitely some of them. Hospitals, 911, a lot of flights grounded.
Yeah, I knew about the flights. That's so you can, if you can't take me to hospital, so be it. But God damn it, I'm going to Miami. Like,
Right.
you got to make sure the planes work.
I got to get to the beach.
Yeah, so it was like Y2K, but it actually happened.
Right.
Because no one, like hundreds of thousands of people didn't work to prevent it specifically, right?
Yep.
It's interesting. Would you put it upon Windows or CrowdStrike, or what? How would you portion the blame out?
It's a good question.
I think this one's on CrowdStrike. Like,
Okay.
Windows allows kernel access, which you can do. Like, I think CrowdStrike did the same thing to Linux.
Yep.
Right before that. So I'd put this on the importance of testing and stage deployments.
Fair enough. I think there is this aspect of like, there wasn't like a button you could hit to like undo a kernel update in Windows. So like, I know with Linux, I haven't really tried these out, but there's like Btrfs and these things that I think are really easy to roll back to previous states. I don't know if that would like fix these issues, and maybe it's a problem if they do fix it, because maybe, you know, maybe you don't want people undoing kernel patches. But I don't know. There's an argument to be made. I think that maybe Microsoft could have better stuff.
I think so. How do you think the news would have gone differently if instead of boot looping into blue screen of death, it kind of either defaulted into safe mode or just didn't load the section of the kernel because it knew what had failed?
Yeah.
Do you think everyone would have panicked in the same way, or did CrowdStrike's stock take a big dip as well?
That's a good question.
Not sure what
see.
it's at now. I think it was down 10% at some point.
Okay. Either that or some intern actually knew about this.
Only 10% is crazy, right?
I mean, for like a $90 billion company or something.
Distribution is valuable, right?
Yeah. It's like, well, are you going to rip it out? Nah.
You could short us or we could fix it. You're
Is CrowdStrike, by the way, before this, I had never heard of CrowdStrike. Is CrowdStrike in this category of companies that, like, if you use it, you get to check off something from a list?
Yeah.
So you're really not, like, it's like, yeah, well, we had to put it in for this thing, and, like, we still have the checkbox.
the government said we had to. Yeah.
Yeah.
I mean, I think they're the market leader in what they do.
Yeah.
Right?
Yeah.
We definitely have customers that use them. So I've seen it in the wild.
Is there an equivalent of that in like electronics or anything like that? Like even for, yeah, I'm thinking, are there like in microcontrollers or processors, are there like requirement? Like, do people do this kind of thing? Put in little backdoors or?
I mean, regulatory capture is definitely a thing. Like there's ISO 26262 in automotive, which Cadence got in there as like some nice regulatory capture. And automotive industry did this to themselves, where it's like, here are these safety things, and if you have software that can verify this, then you must buy that software.
Oh, interesting. So you actually have to buy Cadence if you're.
Well, you have to buy ISO 26262 compliant software.
Oh, I see. I see.
Patented by.
Yeah, you won't guess who the market leader is for that.
Huh. Very interesting. Oh, interesting. Wow. Huh. So not too many equivalents. I remember I used to work with Z-Wave a lot. Have you guys ever heard of Z-Wave?
I've heard of them, but I'm not super familiar. You want to give a 101?
It's a mesh protocol.
Yep.
It's a kind of a layer over Zigbee to make communicating basically between like IoT devices a little bit more standard. And the theory is, like, let's say that this is a big office building. Maybe you want to send signals across the building, but you don't want to install a bunch of hubs for communication. So you just install these smart locks, and they will, you know, transfer the signal around, whatever. Z-Wave kind of I forget the company that owns them. I think it's Silicon Labs, something like that. They made it so that, okay, to speak Z-Wave, you have to be Z-Wave certified, and you need this specific chip.
Yeah.
Yeah.
Kind of
And
like
so,
LoRa has a similar deal with. Yep.
Exactly. So I guess this is kind of the equivalent, but there's no over-the-air updates for this, so you would never get. Not yet, anyway.
Well, that's exactly what I was going to say about the microcontrollers. In terms of security patches, they're, you know, embedding cryptography cores and a whole bunch of stuff, or cryptography peripherals. But unlike our computers, which are constantly network connected and sometimes just don't really do anything if they're not, microcontrollers are kind of expected to be on the same firmware for their entire life and maybe have an update or two. Sometimes a few updates. If you're in automotive these days, obviously Teslas will pull updates for the microcontrollers and that type of stuff. But typically for an embedded device, you just might not ever really touch it.
Yeah.
And that means that, like, if you don't fix what ain't broke, typically tends to keep working. And as far as horrific security nightmares go, I think the things that they're embedded in, because they're typically controlling something physical, if the physical access is a problem, it's typically the only way to reprogram them. If your lock is busted in by the J tag, you're in real strife.
Right.
You can typically access the screws by that point.
Right. So. Interesting. Okay. Really quickly to jump around my train of thought here. So jitX starts, DARPA grants, you're basically building satellites now.
Well, I think aside from the DARPA grant, we built a fully automated design tool in like the first 3 months. So kind of going off the grad school experiences, like, all right, let's make prototyping really fast. So you say like microcontroller with attached sensors, fully automated place and route. And then we tried to sell that, and nobody wanted it.
Really?
The place and route didn't get everyone?
No,
Oh.
because it wasn't great. Right. And the design synthesis was a little simple. And it turns out if you're not within the global, like 10% of the global optimum performance in electrical engineering, nobody cares. Right. So yeah, it was kind of the capabilities you see from any like various startups trying to do automated board design, right? Kind of fully automated prototype level, simple circuits for makers, students who will never pay you anything for anything.
Yep.
Because they're learning or they're spending their time in enjoyment. So not many people pay for productivity tools if they enjoy the time they're spending.
That's fair.
Yeah.
So when did it, what was like the sort of like the innovation that started getting things to click, or like, I guess, when did you feel like it really started taking off?
Yeah, really taking off is like this year.
Oh,
so,
really?
Yeah, one of the first questions Northrop asked us is like, well, will this help us route a memory bus? And they're like, no, obviously, I know you're asking for that, but really your problems are like higher level up, and look at all this like human work that's like, you have senior engineers Googling for parts and like reading 60-page schematics, and like, obviously you have a bunch of problems here. And they're like, oh yes, of course, you're right. No, we needed to route memory interfaces. So yeah, that was the thing to click is push the automation so hard that you get superhuman performance, not just productivity increases, which you would be selling to someone to kind of replace the job of a layout engineer, which you cannot really sell to layout engineers, as people are finding. Surprise. But actually have automation that is powerful enough to let you optimize and build better designs.
Very interesting.
Actually faster instead of like a little faster.
This reminds me of the founders at Synopsys said something similar, where they would like, you know, somebody would bring them a design and they would like redo the design and get it 10 times better, and then people would be like, that's BS. You couldn't have possibly done that. Then they'd go back and be like, wait, you actually did that, and then they'd be like, do it again.
So that was in the later stages. So when they started, Synopsys was powered by VHDL, right, which is a simulation language. It's a terrible language. It's kind of the same as Verilog. But it started getting, their initial designs, they would do synthesis. They said, like, put down the schematic drawing tools. This is crazy. You can't draw a schematic for 100,000 transistors. I know you're doing 10,000 today. That's also crazy. And the initial results of synthesis were not as good as humans, because you'd have designers saying like, oh, I could get that with 3 fewer logic gates. Right. It's not as good as me. But then the design size 10x'd. So not necessarily the quality, but the automation let them do larger designs.
Humans just couldn't keep up.
Yeah. So you have humans not able to keep up with that complexity, and the things about saving 3 gates here and there kind of fell away. But then they built optimization. That was the thing that really took Synopsys through their through early 90s to being like this huge company. It was like they could optimize better. So that's what it became. But it started with like correctness and scaling.
That's so interesting. So like the insight there is kind of, they benefited because the number of transistors kind of took off. And so...
Well, they helped it take off, right? Right. Because they had you didn't have like a big building full of schematics, which is what it used to be. It's pages, layers of schematics on the floor.
Reminds me of, I heard in the early days of Yahoo and stuff, they had buildings dedicated to people who would just sort websites into categories, you know, to try to like augment the search engine. So do you think sort of the circuit board level, maybe it's memory buses, will have a similar revolution just because people are realizing that there are human limitations to some of the things you try to do? Now, memory buses do suck to route, so that makes a lot of sense. Maybe, do you think like more computers, you know, where everybody's talking about AI devices now. So maybe there'll be more complicated computers, and like basically every circuit board design will have a memory bus. And so it's like, okay, this is too much for humans. Or I don't know. What do you guys think?
Yeah, so there's a couple flavors there. So one, you can use automation to move faster than the existing enterprise players and outcompete them on quality of results.
Yeah.
Right. So that's important. I think there's a latent value in mass customization. So like if you lower the fixed costs associated with creating a design, you will get more designs, and that just creates value. Right. And you can also think about raising the level of design of like, can I design an AI device but be closer to the applications level instead of like drawing a board?
Right.
Can I say like make an AI device and sell an AI device? And the closer you get to that, right, or the problem that solves, like the more value you get to capture.
Right. As humans start talking about their intent and not like the very specific things, they're just the focus can shift towards more complicated applications, more complex designs, et cetera.
Yeah, and I think more designs, like I think the factories have done a great job automating, right? And it's like so well that automation is almost commoditized.
Yep.
So you have that support for more designs, but you don't have the designs.
Right.
It's kind of like 3D printers, right? Everyone's like, oh, 3D printers could be like this huge thing. Everybody got a 3D printer, and they're like, well, now I have to do a design.
Well,
and then they didn't.
Well, it's interesting. It comes with the organization. And so, like, I've set up a 3D print lab. My co-founder set up one of the world's largest 3D print labs, actually, for prototyping purposes.
Wow.
And it's incredible because it was like a really sluggish pace. He bought the first printer on his credit card and had the company reimburse it. And he and one other buddy that needed a crank on prototypes were just cranking on the printer. And then their friends adjacent to them saw them exactly what they were doing and went, oh, actually, like, my design, I'm not really sure it's going to work when I send it off to production. So I should probably check it, which is really like the basis of the prototyping. And then they realized something didn't, or that they got excited because they could improve something. And it kind of propagated out as a social wave in a really interesting way. And now there's, as I said, now it's one of the largest prototyping 3D print labs in the world, with maybe one or two other caveats.
Can you name drop this 3D print lab? You're not allowed to.
It's embedded within Tesla.
Oh, so, gotcha.
Yeah. No, for sure.
I was like, why haven't I heard of this company?
No, it's not the company. It's it's embedded within Tesla. But it's interesting to have watched that social wave propagate out because it's really the practice of this. It's you talk about it with electrical engineers perhaps not even asking the right questions when you went to Northrop Grumman. Like, oh, can it route a memory bus? And you're like, well, yeah, of course it can. But like, look at this amazing social practice you've got going. Why are your senior engineers looking at or reading 60-page schematics?
And to be clear, they were right on that one. They were asking the right questions. Like that was what we needed to build to sell this product.
No, for sure.
So like, I thought they were asking because this advice, make sure they're asking the right questions. They're not going to ask you for what they need. But they definitely did. Oh,
I'm not surprised at all that they need it. But once you have it, it's not the ability to do it faster. To your point, it's the like this superhuman propagation that you end up with in your organization. The social aspect that comes after it's the 10x thing that it enables.
Yeah,
so, yeah,
super cool. I did want to. We're sort of like laboring around or jumping around jitX's history, but I'm super curious because you guys released some stuff pretty recently that's really interesting, like, or maybe not recently actually, but you have a free tier now.
That's
right. And so very curious about that and like who should jump into this free tier.
Yeah, so we made a free tier to kind of get back to like, when I started this to help myself as a grad student and help my friends do research. So yeah, I think it's great for students, anyone that wants to like build something, share their code. We have a package manager, so we're going to be showing people like, all right, here's how you design an gigabit Ethernet switch from scratch. And here's how you use all these library elements, and that's going to let you design all sorts of stuff. So I think it's people interested in hardware design, right?
Nice.
So we'll have like probably a lot of projects as well, like probably run some hackathons. So I have like mechanical keyboard hackathon.
Oh, yeah.
Maybe AI device hackathon.
Has anybody built a mechanical keyboard with jitX yet? Me and Matt were talking about mechanical keyboards a little bit.
Yeah, so like this community has made like firmware generators, right? And they also invented their own file format, which is like they have a JSON file for describing a mechanical keyboard. And so, we built a parser.
JSON, thank goodness.
Yeah, so we built a parser for that. So you can just read it in, and it generates a keyboard design. And then you like just pick whatever microcontroller you want with it, and does like the pin assignment, and you can make a keyboard. And fully assembled, that keyboard is like $8.
Whoa!
Not including the switches.
The PCB, yeah.
Yeah, the PCB, but populated.
Yep.
And compare that to most hobbyist keyboards are going to use like an Arduino Pro Micro, which is like $18. So I can get like that processor assembled on a board in like a 5-day turn for like $8 each.
Wow, that's crazy.
It's crazy.
What's the name of this community? If you remember.
The mechanical so you have the keyboard layout editor is like an online editor for this file format. You have the QMK community for the firmware. You have the ZMK community for like the wireless firmware.
I'm so curious. Okay.
Yeah, this is great automation stack. So if you can do the electronics, you can take advantage of like all this amazing tooling that other people have already built.
What's their do they go through KiCad or do they go right to the Gerber? Like, how do you send it to the manufacturer, like from their file format? I'm really curious.
Oh no,
about that
their
a little
file
bit.
format is just for describing the high level layout. Like I have a K key and then I have an E key, right? Not like full design description.
Right.
But you take that as an input and say like, okay, well I can then parse this, combine the standard geometry, and say like, pick your switches, pick your microcontroller, generate a keyboard design.
Super interesting.
Yeah. So we built this, like, we have customers try it in their spare time before like wanting to talk to sales, because like hardware engineers like want to touch stuff without talking to anyone.
All right. If anyone who's listening to this that does not let me buy your product without talking to sales, I'm very angry with you right now.
Yeah.
Period. It should always have a buy button.
The contact button. Oh,
Yeah.
hate it.
Or at least a try button for hardware engineers.
Yeah,
Because
try
like
button. Yep.
we sell to professional engineers, and the person that has to approve the budget is usually someone else.
Sure.
Yeah.
I wonder if anybody's done the list of EDA tools that you can try, because it's not. I don't think you can try. If you're a student, you can get access probably to anything. We were talking about this last night, but like I think I learned in school on like OrCAD or something like that.
Oh, very
It's
fancy.
not. Yeah, right. But it's not very. Not like immediately the first solution that comes to mind if you're just trying to figure out your first tool. I would think. But anywho, that might be a good place. Oh wow, yeah, we're 50 minutes in. Yeah, let's take break. But yeah,
Coming back to you soon.
coming back soon.
You're just going to keep it rolling?
I might just keep it rolling because when I pause things in editing, I'm like, what time?
Pull the camera still on?
Yeah, I might as well, unless they overheat.
Oh, no. But they are rolling.
Nice.
Beauty.
Perfect.